Introduction. I am winning, my son. I just need a 4 on the dice and I will win. Now what will you do?
I know, but let me have my chance.
Okay. Now it's my turn. Oh no! It's 3.
Yippee! I got another chance.
Next time I will get it.
How can you be so sure about the result? Can you predict it?
No, my son. We can just find the probability of the outcome. Probability is the chance that something will happen. In this lesson, you will learn how to find the probability of random experiments. Objectives. At the end of this lesson, you will be able to find the outcomes and sample space of random experiments. Analyze and draw the results of the events in probability. Find the probability of events. Random experiments. In our day-to-day life, we perform experiments like bringing 2 like poles of magnets near to each other. We know that the above experiment may be repeated any number of times. The outcome will be the same. Such experiments are called the deterministic experiments. But we also perform experiments like drawing a card from a well-shuffled pack of playing cards, where the outcome is not certain. Rather, the outcome will be one out of many. Such experiments are called random experiments. Thus, an experiment is called random experiment if 1. It has more than one possible outcomes, and 2. The outcome cannot be predicted in advance. Outcomes and sample space. The possible result of a random experiment is called its outcome, and the set of all possible outcomes of a random experiment is called its sample space and is denoted by S. As you see in the animation, the outcome of throwing the dice are different in both cases, so these are called random experiments. Example. A coin is tossed, and if head occurs, the coin is tossed again, and if tail occurs, a dice is rolled. Describe the sample space of the experiment. Solution. In the first part, a coin is tossed. The possible outcomes are head or tail. If head occurs, the coin is tossed again. So the sample elements will be HH, HT, and if a tail appears, a dice is rolled. So the sample elements will be T1, T2, T3, T4, T5, T6. Thus, the sample space is S is equal to HH, HT, T1, T2, T3, T4, T5, T6. Event. An event is one or more outcomes of an experiment. Occurrence of an event. Consider an experiment of throwing 2 dice. Let E denotes the event. A number less than 10 appears. If actually 5 had appeared on the dice, then we say that event E has occurred. If outcomes are 11 or 12, we say that event E has not occurred. In an experiment, the event E is said to have occurred if the outcome of experiment A is such that A belongs to E. Types of events. Impossible and sure events. To understand it, let's take an example. In an experiment of throwing a dice, we get the sample space as follows. S is equal to 1, 2, 3, 4, 5, 6. Let E be the event the number appear on the dice is 0. It is impossible to get 0 in the experiment. Thus the event E is equal to phi is an impossible event. It is also called empty set. In an experiment of tossing a coin, we get the sample space as follows. S is equal to H, T. Now let G be the event that the outcome is either H or T. Thus the event G is equal to H, T is a sure event. Simple event. If the event E has only single outcome, then it is called a simple event. To understand it, let's take an example. In an experiment, throwing a dice, the sample space is S is equal to 1, 2, 3, 4, 5, 6. There are 6 simple events of this sample space. E1 is equal to 1. E2 is equal to 2. E3 is equal to 3. E4 is equal to 4. E5 is equal to 5. And E6 is equal to 6. Compound event. If an event has more than one outcome of the sample space, it is called a compound event. To understand it, let's take an example. In an experiment of throwing a dice, we get the sample space as follows. S is equal to 1, 2, 3. Algebra of events. Let X, Y be events associated with an experiment whose sample space is S. Complementary events. There always exists a complementary event for every event. For event X, the complementary event is X dash. It means not X. To understand it, let's take an example. The sample space of tossing of 2 coins is S is equal to HT, TH, HH, TT. Now let event X be the event only one head appear. X is equal to HT, TH. The complementary event X dash is X dash is equal to HH, TT. Generally, X dash is equal to S minus X. The event X or Y. Event X or Y is equal to X union Y. The event X union Y contains all those elements which are either in X or in Y or in both. To understand it, let's take an example. The sample space of tossing of 2 coins is S is equal to HT, TH, HH, TT. Now let event X be the event only one head appear. X is equal to HT, TH. Now let event Y be the event exactly 2 head. Y is equal to HH. The event X union Y is X union Y is equal to HT, TH, HH. The event X and Y. Event X and Y is equal to X intersection Y. The event X intersection Y contains all those elements which are common to both X and Y. To understand it, let's take an example. The sample space S of throwing a dice is S is equal to 1, 2, 3, 4, 5, 6. Now let event X be the event multiple of 3. X is equal to 3, 6. Now let event Y be the event multiple of 2. Y is equal to 2, 4, 6. The mutually exclusive events. These are the events which cannot happen at the same time. Let X, Y be events such that X intersection Y is equal to phi. That means X and Y are disjoint sets. Mutually exclusive are the events that cannot occur simultaneously. For example, turning left and turning right are mutually exclusive. You can't do both at the same time. Suppose there is a sample space S as S is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let A is equal to 3, 6, 9 and B is equal to 7, 8. Here A intersection B is equal to 5. Thus, A and B are mutually exclusive events. Both A and B belong to the same sample space, but they are completely different and both cannot happen at the same time. Exhaustive events. When a sample space S is partitioned into some mutually exclusive events such that their union is the sample space itself, then the events are called exhaustive events or collectively events. To understand it, let's take an example. S is equal to 1, 2, 3, 4, 5, 6. Let A is equal to 1, 2. B is equal to 3, 4, 5. C is equal to 6. Hence the event A, B and C are mutually exclusive because A intersection B intersection C is equal to 5 and A union B union C is equal to S. So the events A, B and C are exhaustive events. Example. A dice is thrown and the outcome is noted. Let us consider the following events associated with this experiment. A. Multiple of 3. B. An even number. C. An odd number. Which pairs of these events are mutually exclusive? Solution. The sample space for this experiment is S is equal to 1, 2, 3, 4, 5, 6. A is equal to 3, 6. B is equal to 2, 4, 6. C is equal to 1, 3, 5. A intersection B is equal to 6, which is not equal to 5. It is not mutually exclusive event. A intersection C is equal to 3, which is not equals to 5. It is not mutually exclusive event. B intersection C is equal to 5. It is mutually exclusive event. Assessment. Before proceeding further, let us know how much you have learned. A pair of dice is rolled, there can be 36 outcome. Match the following. Axiomatic approach to probability. Let S be the sample space of a random experiment. The probability P is a real valued function with domain as power set of S and range, the interval 0, 1, such that 1. For any event E, 0 less than or equal to P, E less than or equal to 1. 2. Ps is equal to 1. And 3. If E1, E2 belongs to power set S, E1 and E2 are equally likely if P E1 is equal to P E2 and E1 and E2 are mutually exclusive, then P E1 union E2 is equal to P E1 plus P E2, where P of EI is called the probability of event E. In general, Let S be a sample space containing outcomes L1, L2, L3 up to Ln, that is, S is equal to L1, L2, L3 up to Ln. Then 1, 0 less than or equal to P Li less than or equal to 1 for each Li belongs to S. 2. Summation from I is equal to 1 to n of probability of Li is equal to 1. 3. L1 and L2 are equally likely, then P of L1 is equal to P of L2. Probability events. Let's have an example for better understanding. 2 dice are thrown simultaneously. Find the probability of getting 1. Doublet of even numbers. 2. A sum less than 6. 3. A sum more than 7. Solution. 1. A. Getting doublets of even numbers. A is equal to 2, 2, 4, 4, 6, 6. NA is equal to 3. NS is equal to 36. Required probability is equal to PA is equal to NA divided by NS is equal to 3 by 36 is equal to 1 by 12. 2. A. Getting total less than 6. A is equal to 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 1, 3, 4, 1, 1, 4, 3, 2, 2, 3. NA is equal to 10. NS is equal to 36. Required probability PA is equal to NA by NS is equal to 10 by 36 is equal to 5 by 18. 3. A. Getting total more than 7. A is equal to 5, 3, 3, 5, 6, 2, 2, 6, 4, 4, 6, 3, 3, 6, 5, 4, 4, 5, 6, 4, 4, 6, 5, 5, 6, 5, 5, 6, 6, 6. NA is equal to 15. NS is equal to 36. Required probability PA is equal to NA by NS is equal to 15 by 36 is equal to 5 by 12. Probability of equally likely outcomes. PE is equal to number of outcomes favorable to E by total possible outcomes. Probability of the event X or Y. For non-mutually exclusive events, P X union Y is equal to Px plus Py minus Px intersection Y. For mutually exclusive events, Px intersection Y is equal to 0. Px union Y is equal to Px plus Py. Probability of the event not X. Px dash is equal to P not X is equal to 1 minus Px. Example. A machine operates if all of its 3 components function. The probability that the first component fail during the year is 0.12. The second component is 0.11 and the third component fails is 0.07. What is the probability that machine will fail during the year? Solution. Let E1, first component fails during the year. E2, second component fails during the year. And E3, third component fails during the year. P of E1 is equal to 0.12. P of E2 is equal to 0.11. And P of E3 is equal to 0.07. P of machine will fail is equal to P of at least one of the three components fail is equal to P of E1 union E2 union E3 is equal to 1 minus P of no component fails is equal to 1 minus 0.12 into 1 minus 0.11 into 1 minus 0.07 is equal to 1 minus 0.88 into 0.89 into 0.93 is equal to 1 minus 0.7284 is equal to 0.2716. A card is drawn from a well-shuffled pack of cards. What are the odds in favor of getting a face card? Solution. Total number of cards is equal to 52. Face cards are kings, queens and jacks. Number of face cards is equal to 12. And the cards other than face cards is equal to 52 minus 12 is equal to 40. Hence, the odds in favor of getting a face card are 12:40 or 3:10. In a single throw of 2 dice, find the probability of getting a total of 9 or 11. Solution. The total number of outcomes in this experiment are 6 into 6 is equal to 36. Let E1 getting a total of 9. E1 is equal to 36, 45, 54, 63 and E2 getting a total of 11. E2 is equal to 6556. Since E1 intersection E2 is equal to phi, P E1 union E2 is equal to P E1 plus P E2. P a total of 9 or 11 is equal to 4 by 36 plus 2 by 36 is equal to 1 by 6. Did you know? Blaise Pascal and Pierre de Fermat have given important contribution in the subject of probability. The first recorded evidence of probability theory was found in 1550. Laplace's several works on probability and established many of the techniques and results of statistics. Summary. Let us summarize what we have learned. An experiment is called random experiment if 1. It has more than one possible outcomes and 2. The outcome cannot be predicted in advance. A possible result of a random experiment is called its outcome, and the set of all possible outcomes of a random experiment is called its sample space and is denoted by S. An event is one or more outcomes of an experiment. Types of events. 1. Impossible and sure events. 2. Simple event. 3. Compound event. Algebra of events. 1. Complementary events. 2. The event X or Y. 3. The event X and Y. 4. The event X but not Y. Mutually exclusive events. These are the events which cannot happen at the same time. Exhaustive events. When a sample space S is partitioned into some mutually exclusive events such that their union is the sample space itself, then the events are called exhaustive events or collectively events. Probability of equally likely outcomes. PE is equal to number of outcomes favorable to E by total possible outcomes. Probability of the event X or Y. For non-mutually exclusive events, P X union Y is equal to Px plus Py minus Px intersection Y. For mutually exclusive events, Px intersection Y is equal to 0. Px union Y is equal to Px plus Py. Probability of the event not X. Px dash is equal to P not X is equal to 1 minus Px.